So diffusion reaction, I will just show example of diffusion reaction in Google Colab in Python, how to implement this analytical equation and also how to discretize it. So there is a, I will not go into full details for discretization, but you can follow this example. It's even for Excel. You can even implement in Excel, but I would recommend better in Python. So when we try to discretize this, we are basically making the partial derivatives as deltas and then just rearranging the equation. So this is how then it would look like. You need to discretize the x and also the space and also the time. So we have the delta x and delta t. So it's a two-dimensional grid for space and time. And when you define these vectors, then we just go cell by cell and implement a function, which is a straightforward. That's why it's called also explicit method, because you just write a function and then calculate the values of new results based on the previous ones. So this is how the Euler method works. So what I told you, we just do the deltas here. So the new time steps minus the previous time step. This is now delta t. The partial derivatives became the deltas, algebraic equations. So it's just a set of algebraic equations for each node. And in explicit method, you can then explicitly calculate the new based on the previous, on the old one. And here you have the space discretization. So the space, the second derivative, if you check in the Wikipedia or any textbook, you will see how you can discretize this. I can show you how the molecule should look like. Maybe let me show you. I don't know, just Wikipedia, you can see this. Not this one, but yeah, explicit method. I want the coefficients. Where are the coefficients? No. Yeah, this finite difference coefficients. So just so you based on the how accurate you want. This is central finite difference. If you want the first derivative or second, so we want the second derivative, second order accuracy, and you will see the coefficients 1, -2, 1. So even not knowing how to do it by hand, you just can check the table. And this is the 1, -2, 1. So those are the coefficients. If you have a higher order derivative, then you would have these coefficients, for example, third order derivative, or you want higher order accuracy, then you need 4 nodes, 1, 2, 3, 4, 5 nodes actually, fourth order, and then you just plug in these coefficients. But now we will work on second order accuracy. So we just need 1, -2, 1. So this is the left neighbor node, this is the central node, this is the right neighbor node. So this is where how you get these coefficients here. And then you just need to explicitly write it for j + 1 and then as a function of previous time step. So this is the explicit formulation for Euler for finite difference for partial differential equation for our diffusion. If you want to know implicit method, then you need to solve, you are solving the system of equations, because then you have here j + 1. So the j plus 1 is a function of j plus 1, so the next time step is a function of next time step, so you cannot solve it explicitly cell by cell. You need to solve a system of equations, what we did the first day, solving a system of equations, linear system of equations, so many equations as many nodes, so you can solve this, what you solve on the first day, how you solve that when we were balancing the equation, balancing the chemical equations. So it's the same here, you just get linear system of linear equations and then you can solve them, and then you also know how to solve implicit. So you just, if you would have here j plus 1, you would have an implicit method which is more stable, but now I am just showing you how to implement the explicit method. And then you should be careful about the stability criteria. So you should choose small enough time step that you don't have instability. This is the criteria how to choose the time step. So it depends on the finer the mesh, also the finer the time step, no, the bigger the time step you can use, no, the finer, yeah. The finer the mesh, you also need the finer time step, but you are more accurate. And it's, if you change the diffusion, so the transient behavior, the dynamic behavior of this equation, you are also have to change the time step. So this is like the minimum time step that you should have to be stable. Okay, now I will not explain this. I will go, you can implement it in Excel. Then you just follow this. So you can see here we have, you know, the boundary conditions, the 3%. This is the inner wall. So we will put just 0, or we can put, you know, adiabatic boundary condition. And here we have the initial condition. There is no chlorides in initial condition. We have the 3% like a step function boundary. And then we calculate cell by cell. Those are the inner nodes that we need to calculate. And you calculate cell by cell. The next cell you calculate based on the previous cells. So you start with this one, you have the previous nodes because they are all 0. So you just propagate and calculate cell by cell. First you do it for all the elements in first row, then you switch to the second row, that means the next time step. And then you do all the space steps, and then you go to the next time step. So this would be some time step in after some few time steps, and you are calculating the value of this cell based on the previous 3 cells. So you know the values and you can do explicit formulation, and then you just calculate for everything. So it's a nested loop. This is the molecule. It's called the molecule that you follow because it's repeating always the same. You just change the indexes. So now let's see how this would look in the Python code. So if we open here the code, first I show you how to implement the analytical solution. So we have the parameters, the reference diffusion coefficient. We have the, how to make this bigger. We define the initial condition, the boundary condition. Initially everything is 0. We can, I think we have all the parameters. And then this is the x discrete vector discretization. Step is 0, 1. No, from 0 to 1, 0, 1 meter. This in 100 steps. We define the years we want to simulate, and then we have the time discretization. So it should be in seconds, so we are converting years into seconds. And then we have our function. which is diffusion coefficient as a function of time. So we can define this function. And then we calculate, I called it reliability because you can also do the statistical later. But now it's just deterministic. And here we can do our explicit so we need to loop for all the time points, and also we need to loop for all the space points. And then in this double nested loop, so we can do the equation which is here. This is okay, sorry, this is not this is the analytical solution. So we only have the yeah, actually we also need to loop both, yes. But then we just call the function and the equation, analytical equation that we are solving is this one here. So it's error function. We have the error function. There is a definition of error function in CPy library. And those are, the t is the vector and x is a vector. So we get the concentration, which is a matrix actually, for all spaces and all times. And then if you plot it, you will see a result like this. We plot the analytical solution for 25, 50, and 100 years. That's why we are looping the time. And we do it for all the space, the penetration depths. So this is the analytical code, and then we can compare it with the finite difference. Same parameters, input parameters. Again, we need to define the function to calculate the aging diffusion coefficient as a function of time. And then we enter the time stepping here. And here we have the molecule. So the discretization molecule, if you remember. It's this molecule. So we need to have the concentration at j time step and I minus 1 space. So it's like this in the Excel. So this, yeah, we just write the molecule. So it's a two-dimensional matrix. And we calculate for each time step and each. So this is a space dimension, and we are storing that in for each time step. That's why we have the copy here. And then if we run this, we will get this result, and then we can compare analytical and finite difference. And you will see that actually the analytical is not the same as finite difference. And this is probably because you can maybe increase the number of spatial points, and maybe even the number of to 300, from 200 to 300. Let's see if that affects the accuracy. And we can even increase the time step, decrease the time step. E on minus 4. Let's run it now. Now it takes longer to calculate. But actually we want to run this one to compare. And he is taking all the parameters from the previous. So let's run also this one. And let's try to run all. Now he is complaining because they are not the same dimensions. So we should also change the dimension of the analytical. Let's keep it back because I think the error is the difference between analytical and numerical. It's because I would trust the numerical, meaning the finite difference, because I'm not even sure if this analytical solution with the time-dependent diffusion coefficient, if this is really a true analytical solution. Because this is added, the diffusion coefficient is changing with time. This was added later, and I am not sure if this is really a true analytical solution. So probably you need a better analytical model, which is the true analytical model of the numerical of the partial differential equation that also changes the diffusivity with time. So this is why there is a gap here. So that's why you need also numerical solution. Probably if we would not change the diffusion coefficient with time, we would get same result. But because we are changing the diffusion coefficient with time, then the analytical solution actually breaks. It's less accurate. But there are better analytical solutions that you can find in that book from the technical committee, chloride ingress modeling. You can see also other numerical solutions. Any questions here? Did you manage to run this one? I hope you can run it. If there are no questions, we can continue to thermodynamic modeling. I'll wait a few minutes for some questions. Before we switch the topic. I didn't hear. So in the chapter 2 of that book, written by Lars Olof Nilsson, famous guy in moisture and chloride ingress modeling, he did very nice overview. And here you can see this overview of the models. So we have the error function with constant diffusion coefficient. So the true solution is when you have the constant diffusion coefficient. Then you have the error function with time-dependent diffusion coefficient. But this is the average diffusivity, and that's probably why it's in the time interval 0 to t. This is why we have this difference. So this is the time dependency. This is the Durac model. If also you can expand it. And then we have they call it false error function solution with time-dependent diffusion coefficient and surface concentration. Even if you have time-dependent surface concentration, but you see that such equation is not mathematically correct solution to fix second law. It must not be used at all, and certainly not for prediction beyond test data, because it's not a fundamental solution of the diffusion. He calls it false error function solution. And there is a model that did correct error function solution, where you can have a variable time-dependent surface concentration and time-dependent diffusion coefficient. So actually you should implement this function. You have this special function, which you can see here below. And then you can implement also correct analytical solution. But I think then it's easier to implement numerical, find a different solution. Otherwise you have to catch this function. To me, it would be easier to implement numerical. And then you have the numerical solutions. So it's a moving boundary problem. Basically, you get a square root law. So even this very simple square root law already defines. And in physical models, we have this more advanced model, multi-species model. So that not only chlorides, but also alkalis, all the species, they travel together. And they actually affect the diffusivity. Because all the ions, they have different speeds, and then if you have different speeds, you have potential, which then affects the diffusion of each ion. So it's an Ernst-Planck equation. You need to have this potential for each ion, so it becomes very advanced modeling. You have the binding isotherm, nonlinear. You can couple it with thermodynamic modeling. Here is a stadium model, finite element, very advanced model. Also Johannesson, he did a lot with this multi-species, it's called multi-species model with binding. Then you also have the water effects. So you also need to do the moisture transport. And this is what Nielsen did a lot. Coupled moisture and chloride ingress. So this was just an overview of the models, which you can now implement also with finite difference and also analytical. And with this, we are finished with the diffusion models. So if you have questions now on the diffusion modeling. So now you know how to implement finite difference. You have the code. You also have the Excel example. If you want, you can even do it in Excel. You can do, now you can basically solve any partial differential equation, also with reactions, with any accuracy. So if there are no questions, you're not so motivated in solving differential equations. But if you are, there is also a Ryland course, what I mentioned we have on numerical modeling, computational methods, where we have 5 days, full day course on computational methods. So there you can learn more about this, how to implement computational methods. But here we can then go back to our CemGAMS app. So if you want, you can open. I will show you how you can now use your durability phase assemblage to model the ingress of or leaching. Let's do first leaching. Or if you want, we can even do first blending. I think I didn't show you that yesterday. On Tuesday, I mean. You can see how also the blending. So the more Putzolan you put, how that affects the phase assemblage. So you can put here a new recipe. Let's take LC3 if you like. That's the most interesting. Here put some name, because then you will have it here. You will have here the the recipe and your the number or anything that he can run. And then we can also run the process, and now we put here the blending, not the hydration but the blending. So he is adding STMs, so we can, we did the hydration, then you will get a phase assemblage as a function of time. But here you can also put blending. I didn't show that on Tuesday, so we can see how the phase assemblage, how Portlandite is consumed as a function of amount of added SCMs. In here you can also put your name for the process name and then simulate. And then we can see how our Portlandite here. This is the Portlandite, how the Portlandite is consumed by adding SCMs. In this case, this is clay. Because we define the SCM here. If you go to SCM, and it's probably it's a combination of limestone. Yeah, it is. So the SCM here is the limestone and calcine clay, and even gypsum. It's part of the SCM. So by adding this mixture of LCA, so the combination of limes, this 20% of, now I'm not the unit exactly, gram mole fraction, what is he exactly adding? So you can see this here in the process blending. Then if you go into the process, linear addition of 0 to 20 gram of SCM of composition set in the parent recipe. So that was here above. So we are actually adding 0 to 20 gram of SCM in this mixture, and then we can see, so it's gram. The unit is gram of SCM added, so 20 gram of the total SCM, which is limestone and metakaolin and gypsum. So 20% actually almost consumes the whole Portlandite. If you want to change this to see, I don't know, until 40, what was the final? 46.1. You can add this here. You can even change the number of steps. Let's leave it. And then if you run again, the process, simulate process again. Now he should go to 46. Let's see if he's still simulating. Yes, now we have till 46. So the Portlandite is, where is it? Portlandite is calcite. This should be Portlandite. Streetlingite. Ah, this is Portland. Or no. Ah, this is the amount of. Ah, it is clay. Okay. So it says here that we have cement, unreacted cement, and this is clay. But no, the SCM is the total amount. Okay. So we have also we have the limestone. But I don't know what happened with Portland. And here is calcite, limestone, Diffusion. So when you sum this, it's in volumes. Let's go to mass. So now here we have the mass. So this calcite clay is 19, but it's stacked. So let's don't do stacked. Let's do this is solids. Stacked area. You can choose if you don't want stack. You can, I think, change here exactly. Then you have. I think now it's not stacked. One on top of each other. Just it's still stacked. Let me check. Calcite, monocarbonate. Here is Portlandite. You can click here, then it disappears and appears, so you can find it easy. So we can see how the Portlandite is fully consumed when you have 28 grams of total SCM. But now the question is this stacked or the true value? I think this is now not. Now it's how we can check this. Calcite clay starts from 0, so this is not stacked. I don't know why it's still here stacked. When you go to composite line, you don't have the stacked. What did I? Where is my result now? Let's do simulate again. It was here. Okay, I pressed. So when you put composite, then it's not stacked, and then we can check the sum. If you have the sum of, 20 grams of calcite clay, 20 grams of calcite clay. We have limestone. Where is limestone? Calcite. This one is limestone. So additional 13 grams, 14 grams of limestone. So 20 plus 14 plus gypsum. But this was minor. So 20 plus 40, so it does fit. So it is the total SCM. Here we have the total amount of SCM, which makes sense because here the SCM is defined as a sum of limestone, calcite clay, and gypsum. A little bit of gypsum. Mostly it's calcite clay. So this, what you have here is the sum of the total SCM. So now you can also do, I don't know, you want to do it, you can also do it with rice husk sketch. That's maybe interesting for you. So we could go to recipe. You just need to define your Which one is with silica film? Yeah, that's a good question. Maybe we should define one. Yeah, we can take the flash and then kick out the flash and say it's silica film, which means rice husk ash. SEM2 is limestone. SEM3 slag. Let's try this SEM2. Let's call it rice husk ash. So you can see the minerals, SCM. What do we have? Limestone and fly ash. Okay. So now we can add. You can even change the name. I will not change it now, but you can change it. I think the composition is mostly silica. This is also maybe a little bit lower for rice husk ash, but it doesn't matter. You know now where to change it. So you should change this composition. You can rename here rice husk ash. And we can say, I don't know how much you want inside. How much do you usually put? Probably 10%. Otherwise you jeopardize the rheology. Maximum probably less. So we can put this to 0 and put this one to 10. Actually, it doesn't matter. We can see the and limestone. You probably need some limestone, but let's put some 0 anyway here. So now you can equilibrate this. This is your rice husk ash binder, and now we want to see the effect of blending with adding rice husk ash. You can put simulate. So you should always change this because this is what then he's taking in the simulation. Now we changed it to he puts 100%. I think I put 10. It doesn't matter, but we can see here, yeah, from 0 to 20 gram of rice husk ash. You are how the phase assemblage is changing. Where is the Portlandite? Here. Okay, so it is the blue one. I don't know why is he. Yeah, this is the Portlandite. So you can consume the whole Portlandite when you have 7%, 8% of 8 grams of rice husk ash in 100 grams of binder. I think it's binder. Added SCM onto hydrated, not blended cement. Resume masses. Yeah, you can see here, it's the 100 gram of, this is chemical shrinkage, I think. 100 gram of hydrated binder. Added SCM onto hydrated cement. Yeah, this is then 7 grams per 100 gram of paste. So you need to recalculate the per gram of cement to be able to recalculate the replacement ratio. Okay, did I solve your rice husk ash case? So very easy to do it in this. You can see the reactivities. And you can change the kinetics. Where is the SCM? SCM is here now. Okay, then you need to, if you want to see the reactivity, you should go back to hydration process. Yeah, this is what you should then also do. You should go to, because this is what I showed you is just the final composition. And I think final is 28 days because it's defined here. Probably it's 28 days. You can see it here, blending SCMs. Let's run it one more time so that you know. Ah, yeah, here, reaction extent value given for 28 days. I think this plot is for 28 days then. SCM set at 20 degrees, constant binder mass. Composition and reaction extent of SCM material, water binder, temperature must be set in parent recipe task. But we can also check it here. So if you have without, let's check it here. Why is this 100? So let's equilibrate our 28 days. Forty 41, let's say, milliliters. And here we have 23. So yes, you will need to, equilibrium is at 28 days. And blending, the question is this also 28 days? This is what I am trying to figure out. But probably the easiest way is just to watch the video and check the tutorial here. In this question, you can check what is the, if he is taking also 28 days or he's using the final time. Effect of systems, yeah, it doesn't say here. Okay, so you need to check this to know what are, maybe in the table results we have the values. No, not really the units. So you need to check this in the video. What are the units real? The real meaning of the units. Or just, I think already here you can see the process. Semen hydration. Blending. 20 gram with increment of 0 to 2 gram. All per 100 gram of cement plus SCM. Okay, then it is per 100 gram of binder actually. Keeping the initial binder mass and water binder ratio constant. but it doesn't say. It's probably for the, like here, he says it's 28 days time, but for this, maybe we can see it from the reactivity actually. This is what I wanted to. But then we do different process, okay. But we can check actually, because then we know the reactivity. But if we have here reaction extent, we know the reactivity. Halite, aluminate, ferrite, halite, and it's completely reacted STM probably. I mean, the degree of reaction is here. And here the reaction extent is 0.876, and then we can check here. What is the degree of reaction? 0.876. So it's the final. It's not the 28 days, it is the final. He's using the final equilibrium value, not 28 days. So here he shows the values for 28 days. But here what he's taking is the final equilibrium. That everything reacts. So this is for full reaction. Also for ACM and all the cements when they fully react. And I wanted to show you the degree of reactions, so then you can go to the process, new process. Rice husk ash, but we want to change. Probably we need a new process. We want hydration. Rice husk ash. He will take now he knows it's this. He always bases it on this recipe. And then simulate. Okay, now we should get the kinetics for Raskai's cache hydration. And if we go in reaction extents, it's a bit weird. I think maybe best to start a new process again. I think here should be time, right? So now he's a bit mixed. Let's start from a beginning. Okay, and now the hydration. But it's showing time. This has to be time. And then if you go rates. Now he's showing the addition. Something went wrong. I don't know what. Then you can send email to the guys and say that there is a bug. And actually they will reply to you. Kulik, probably. So we just found a bug in the... Let me see. Let's just take new. Write it. Aha, maybe, yeah, okay. Maybe we should take this one. Ah, that's why. We should take the hydration MPK. Yeah, that's probably the reason. New. Okay, let's then go back and take our rice husk cache example. Then process, new process, hydration MPK. That's the kinetics. Don't take this hydration, take this one. And then new. Aha, what do we want? We want time lock, okay. Simulate. Now we have the lock time, okay, yes. So now we can go to rates, reaction extents. Okay, now we have the kinetics. And this is rice husk ash is this one. Yeah, it says fly ash. We didn't change it. But this can be your rice husk ash. You just need to change the name and the value. And the composition and reactivity. Let's, yeah, if you want, I can demonstrate. Let's change the, yeah, let's say that let's keep rice the fly ash. You just can write here rice husk ash. We can, you can change the composition of your rice husk ash. We can check the degree of reactivity. This one only goes to 0.2. You can now increase, I don't know, to 0. This is quite, can react a lot. 0.8. We equilibrate. And then we run the process again. Simulate. Now this will change. Now it's called rice husk cache. And it should have taken these values from this table. That it reacts 80%. Let's see if it did react at 80%. How to get that? No, it reacted only 44% after 10,000 hours. Why is that? Probably the kinetics is too slow because he's following the kinetics. This is the maximum. This is the maximum possible, but the kinetics allows it only to go to 43. So now then you should change the kinetics. Yeah, this is a good example that we go everything through. Then you should change the kinetics here. And then you should increase the this one. You should change it to for rice husk cache. But he still takes the parameter from here. I hope. And then which parameter we should change? Good question. Here I would know, you can change, nucleation, diffusion, I would change the diffusion. Okay, 3. But here I actually, you can maybe use easier. Yeah, now you need to play with this. Yeah, let's just try to change some values. Let's put here, I don't know, 90, 91. And then we run the process again. And by some logic, now they should increase. But you should, yeah, it decreased, of course. Now we reached 70% degree of reaction. So you should have some data points here, and then you can change your parameters. You should have a look how this function is defined and how the parameters are changing the shape and height of the function. So you know what are you changing, and basically you want to fit your points that you can get the good. You can fit your experimental data, changing these parameters. You need to know reactivity, or you can actually change it by fitting the Portlandite content, because this is what you can measure by TGA. The Portlandite, where is it? Here. Yeah, this one. So here, this one you can measure with TGA, and then you can change the reactivity of metakaolin of rice husk cache to match this Portlandite value. So I think now I solve. This is the full case solved for rice husk cache. Any questions here? If not, we continue with the durability. This was the main, but it's very similar. Now you know how this runs. So let's now take a new process. What do you want to simulate? Do you want aluminate cement or calcium sulfoaluminates, or you want LC3? Now let's take L03 system. This is, I think, interesting for you. And then, yeah, there is no geopolymer. And coming soon, I hope. And let's do, I don't know, CO2 attack. Let's do CO2 first, then we do acid. So let's equilibrate the LC3 system. Then we go to process. Let's first see what we simulate with the hydration. So basically we have some Portlandite still, or not. Let me check. Basis to, no, very little amount of Portlandite. So should be very durable mixture. And then let's see, now we want to simulate CO2 attack. And then actually you should go here and salts, because the salts define what is the ingress. Or we can do leaching first. Then you don't need the ingress of chemical ingress. We can do the leaching first. New process. Let's do the leaching. Add water. So we are adding water and seeing how much of the ions are leaching, and then the dissolution of the hydration products. So leach. You can simulate the leaching of LC3. I didn't see this yet in literature, so maybe nice to publish paper on this. You just need some experiments. So you can see how the volumes are changing, how the Stretling guide, all the phases are dissolved when you put a lot of water on top. That's why here you basically even don't see, it's a lot of water inside. You even don't see the phases are here below. So we put a lot of water. You can change this, how much water you add. Adding water. So here you can volume, you can change the volume. Volume stop 6. So this is what, 6 liter or 6 something. Volume. Yeah, this is only solids. Total volumes. What is this? 6 million milliliters. 1 million milliliters. So 1 liter. Oh, but we had 6 here. 2 to 6. This is step 1,100 steps. But it's logarithmical. Okay, so that makes it difficult. Yeah. To predict what he's doing. Let's do linear. Then it's easier to see, maybe. The volume should be here, which is basically the here. Yeah, it's 1 mega milliliter. I would say it should be 1 liter. Target unit grams. Okay, so it's 6. Volume 600 kilo milliliters. Let's do grams. $400 kilograms. 400 kilograms of water. You need 400 kilograms of water to leach so many phases out, to dissolve the phases. Yeah, you can also change water cement ratio. I don't know, clearing. I don't know these parts. But let's go to other process. Then we can have a. So this was leaching. We can do ingress, and then if you do ingress, add salt. You are adding salt, and this salt is defined here. So this is what he will add. He will add CO2. We can also do sea salt. But let's do the CO2. Let's see how the LC3 system endures carbonation. And this will be CO2. I think it's pure quantity CO2. Let's see what it is. Yeah, it's 100% of CO2. We can do 20% if you want to simulate the flue gas from the cement plant. So this CO2, 100%, pure CO2 addition, simulate process. What's he now complaining? Okay, you need to put, you cannot. Yeah, he wants, he doesn't like spaces when you name it. But he changed it, but himself. So now you can see by adding 10 grams of pure CO2, this is what you will increase the calcite content, of course. You will dissolve some hydrocarbonates, you will dissolve CSH, you will dissolve stretlinite, you will dissolve monocarbonate, and you will increase calcium carbonate, monocarbonate you will also dissolve. This is the aqueous solution with CO2. Let's see pH maybe. The pH is still high, but it decreased a little bit. So we need much more CO2. And that you can change again in the process. Where was it? Here. So we can change the adding salt. So this means now it's adding CO2. 10. Up to 10 grams. Yeah, this is gram. Okay, so last time this. So we have we added 10 grams of CO2. Now we can do up to 100 grams of pure CO2. And let's see how this changes pH. Simulate. You are not doing the example, I see. Yeah, this you need to play with this. Yeah, you can also play later, no problem. It's then you need to watch the videos from Kulik better.